what are the units that we can use to measure the energy transfer. And for the exothermic, endothermic reaction, we need you to be able to do these kind of calculations. Okay, we will look at the calculations again later on in the next, in the third and fourth learning objective in this chapter. But first, when we're looking at, in the second learning objective here, we want to introduce an equation so that we can quantify the amount of energy transfer for a particular process. That is, the Q equals to M times CS times the change in temperature. So the thermal energy and heat transfer has something to do with the temperature difference. So if you measure the temperature before and after and you see a difference there, well, that means either there's energy coming in, you see the temperature going up, there's energy going out, you see the temperature going down. So the amount of energy transfer can be calculated, can be quantified by this equation. So this equation is something that we want you to be able to use and do calculation on. Okay. So in this case, the heat exchange happens when you have an uneven amount of, when you have a difference of the two objects that has a different amount of temperature there. So heat is the form of thermal energy, can be exchanged between the systems surrounding. Okay, so that's the first thing we want to point out. And then heat exchange occurs when the systems surrounding have a different temperature. And the thermal equilibrium will be reached, meaning there will be no more heat transfer if the system surrounding reaches the same temperature. So if you have, say, a cup of cold water, a cup of hot water, you mix them together, eventually the mixture will end up with a particular temperature. That particular temperature is the temperature that, well, the colder water that you mixed before you mix the cold water and hot water together, the lower temperature, you will not be able to cross over that thermal equilibrium, the temperature when the thermal equilibrium is reached there. So the temperature is the measure of the thermal energy with the sampled matter there. So heat flows from a matter with a high temperature to a matter with low temperature. Okay, so when you reach the same temperature, the temperature will not cross over. And when you reach the same temperature, when the hot and cold object reaches the same temperature there, we say that we reach thermal equilibrium. So this is what governs the heat transfer. You have hot water, you have cold water, you mix them together. Eventually, the amount of hot water, the amount of heat given out by the hot water equals to the amount of heat obtained by the cold water. Or for that matter, if you have a piece of, a cube of a metal block, you heat it up, and the temperature, say, go beyond 100 degrees Celsius, and then you have a container with some water there. You drop that metal block into water, and obviously the heat will be transferred from the hot metal block to the water. Eventually, the metal block will cool down. Water temperature will warm up. Eventually, you reach thermal equilibrium. Now, in that process, the total amount of heat released by the metal equals to the total amount of heat obtained by water. And though metal may have a different mass than water, so the equation that we can use is that we can actually calculate the amount of heat transferred equals to C times the change of temperature. C is what we call heat capacity. Okay. Now the heat capacity as a unit of either degrees Celsius or the heat capacity as a unit of joule per degree Celsius or joule per Kelvin. Now in this case, we can use either Celsius or Kelvin because Kelvin and Celsius, they have the same scale. They just have different, when you, 1 degree, the difference between, the Celsius and Kelvin, it's the same there. 1 degree Celsius equals to 1 Kelvin. Okay, well, the difference there is that 0 degrees Celsius is 273.15 Kelvin, but they are running on the same scale there. So whether it's Kelvin or Celsius, we can use either number script. Okay, it's joule per degree, Kelvin or Celsius. Okay, so in this case, Q equals to C times T. The larger the heat capacity of the object being studied, the smaller the temperature rise will result. Will be for a given amount of heat there. Okay, now heat capacity. This is without specifying how much in terms of grams, how many grams of the sample that we have there. Now, we have them when you deal with, say, a larger quantity of hot water will have more heat in there versus a smaller quantity of hot water when their temperature are the same. So we have to quantify, we have to specify how much material that we're talking about, in moles or in grams. So in this case, we want to introduce another factor there. We call it specific heat capacity. Specific